In this video, we are going to test for the assumption of equivariance, also called homoskedasticity in linear regression, using STATA. We have previously checked for the assumption 1 and 2, and we shall be checking the rest of the assumptions 4, plus multiple linearity and outliers in our subsequent episodes. So consider liking and subscribing to the channel so that you don't miss out any of our episodes. For you to use linear regression, it is assumed that the variance of the error terms remain constant as the independent variable increases. So you have to check for this assumption before running and interpreting results of linear regression. There are three main ways how we can test for this assumption. One of them is using residual versus fitted plots, or RVP plots, which are basically plots of the residuals from a linear regression versus the predicted values of that model. Another way of testing for equivariance is using the residual versus predictor plots, which are basically plots of residuals from the linear regression model and each independent variable one at a time. Then we also have the statistical test, the Breusch-Pagan Hooke-Weisberg test for heteroskedasticity. So we are going to first run the residual versus fitted plots and the residual versus predictor plots because they are found within the same dialog box in STATA. We shall come for interpretation. Here is the hypothetical dataset that we shall use to test for assumption of equivariance in linear regression. We have the outcome variable, which is systolic blood pressure, numerical in nature, which is a requirement for linear regression. Then we have got two independent variables, that's age and BMI. So in this model, we want to determine the relationship between age and BMI versus our outcomes, systolic blood pressure. To do that, we have to first check for the assumption of equivariance of the error terms using the RVF and RVP plots. To obtain these plots, we have to first fit our linear regression model through statistics, linear models and related, then linear regression. From this dialog box, we shall specify our outcome variable, then our independent variables, age and BMI. Then we click OK. Here is our output for linear regression analysis in STATA, but our interest is not to interpret this output at this stage. We only wanted to fit this model so that we are able to get the regression diagnostics to check whether there is the assumption of equivariance of the error terms has been fulfilled using the RVP and RVF plots. To obtain these plots, simply go to statistics, linear models and related, then regression diagnostics, and then we select the residual versus fitted plot. We also have the residual versus predictor plot. Let me start with the residual versus fitted plot. And once you've run this model, here STATA is telling you that graph a residual versus fitted plot after a regression, a linear regression, or an ANOVA. So you can only get this plot after fitting a model, which we've done. So just click OK. This is our RVF plot, residual versus fitted values. As you can see, we are interested in data points that are randomly scattered around the zero line. As you can see from this, we can say that our assumption has been passed. Then we also run the residual versus predictor plot, still through statistics, linear models and related. Then we go to regression diagnostics, then residual versus predictor plots. In this one here, we run one variable at a time, as opposed to the residual versus fitted plot we've just looked at, which is for the entire model, plotting the residual values versus the fitted values for that model. This one tests one variable at a time. So we shall start with age, click OK. Here is our residual versus predictor plot for our independent variable, age. Here are the two graphs that we've just run. So for RVF, if the cloud of points looks like random noise, that's good. The assumption has been fulfilled. There is constant error variance. Similarly, if we look at the RVP plots, a good predictor forms residuals that are scattered randomly around 0 or no pattern. In other words, you can also look at it, the interpretation in this way, that the variance at the start or for lower values of the variable age remains the same. The vertical distribution of the variance remains the same even when the variable values increase. That's the constant variance we are talking about, or homoskedasticity. So far, using the two plots, we can see that our equivariance assumption has been fulfilled. On the right, we can see an example of an RVF plot with a violation of equivariance. You see that if we have a distribution like this, where the error terms, instead of being randomly distributed, you can see here they start as if they make a funnel shape. That would be a violation. Similarly, for the residual versus predictor plots, this vertical distance or distribution here, you see that it is not the same as the values of the x variable or our predictor increase. You can see as if there are seasonal variations. Here it is low, high, like that. So that would be a violation for this assumption. Now let us look at the statistical test that you can use to test for homoskedasticity or equivariance assumption in linear regression. So to run this assumption, you should have also first fit the model, like we've done here. If you're not sure whether you had already fit the model, still you can just go back to this. You can use this command, enter, to run the model just to be sure. So to run the statistical test for checking for equivariance, simply go to statistics, go to post estimation, then you go to specification, diagnostic. Then here we have tests for heteroskedasticity. So you're going to click on it, and then it is the one selected. Then just click OK. So here we have the Breusch-Pagan Stoll-Cook-Weisberg test for heteroskedasticity assumption of normal error terms. The null hypothesis is constant variance. So the overall p-value is here above 0.05, indicating that we fail to reject the null. Here we are interested in a non-significant p-value for that assumption of constant variance to be fulfilled as our null. That is for the overall model. However, if you have some variables which you could not determine from the graphs whether they have passed the assumption or not, you could still run the same test for those particular variables by going to statistics, still post estimation, and specification. We are testing for heteroskedasticity here, and then instead of use fitted values of the regression, this time we are testing for a single variable. If we are not sure whether age was passing the assumption through the graphical approaches, then we can just test it one at a time here using the statistical test. Then we click OK, and we can see that the p-value is also above 0.05, the usual alpha value. So age also passes this assumption of equivariance. If you found this video useful, consider liking and subscribing to the channel so that you don't miss out any of our episodes. Next, we shall be looking at another assumption of linear regression, which is normality of error terms using STATA. See you in the next episode.